So in this session we are going to discuss about the first order system, right. So first order system, a system, how it is formally defined, a system for which the input and output variables are related through a first order differential equation. So a system for which the input and output variables are related through a first order differential equation is a first order system. So you see that we have A1, or directly I am writing in terms of deviation variable, A0 y prime equal to B f prime t, where in time domain schematic we can think of y prime t and f prime t. So that is a first order system. So you see that here we can have two possible cases. When A0 is equal to 0. So A1 dy prime dt equal to B f prime t. So dy prime dt equal to B by A1 f prime t. So we write dy prime dt is equal to Kp prime, a system specific constant, into f prime t. So taking the Laplace transform, because we have to go for this input output model of this first order system. So using Laplace transform, we have s into y prime bar s equal to Kp prime into f prime bar s. So the respective transfer function Gs is y prime bar s divided by f prime bar s equal to Kp prime by s. So now you see that its transfer function, the respective form is pretty simple. So let us see how this type of first order system will behave when it is given a step input of its variable f prime t. So let f prime t equal to 0 for t less than 0 equal to a for t greater than equal to 0. So f prime bar s is a by s, and essentially y prime bar s is equal to Kp prime a by s square. So that is the typical step input and it is the Laplace domain output. So using inverse Laplace transform, we have y prime t equal to Kp prime a into t. Now that is the dynamic response of that system, it is linear. So what is actually happening? Try to understand. T and here f prime t, that is the variation of the input. Step and step height is a, and this is t equal to 0. So this is the input function. Now the output is something like this: t equal to 0, t and y prime t. Now you see this sort of first order system is called pure integrator. Why? Because if we consider a time t, the integrated input variable up to time t, that is 0 to t f prime t dt, is a into t, and y prime t is kp prime a into t. So in a sense it is proportional to 0 to t f prime t dt. So this type of first order system is referred as pure integrator. Right. And as if it integrates the input to generate the output. Now example, you see we have a tank, input Fi, right, and here instead of a valve we have a pump where the outflow rate is F naught, and that's constant. It's invariant with time. It's independent of how this Fi changes, because there is no manual or controller intervention, right, unlike valve. So the system equation, if the cross sectional area is A, so A into dH dt equal to Fi minus F0. So steady state equation A dHs dt, which is 0, Fis minus F0. So if I subtract, we will get A dH prime dt equal to Fi prime. So that's pretty simple, and if we take the Laplace transform, As into H prime bar S is equal to Fi prime bar S. So the transfer function Gs, which is H prime bar S by Fi prime bar S, becomes 1 divided by A whole bracket S, or denominator S. So Kp prime, the system specific constant, is 1 by A. Now these sort of systems, you see what will happen if I increase Fi by a step. Okay, let's say this is Fi prime, this is t equal to 0. So what will happen to H prime? Grow, and it will saturate. Why? Because if this level is H, beyond that it cannot increase. So it will grow up to H, right, or rather this is H minus Hs, and this is t equal to 0. So it will grow up to this H minus Hs, because originally the level was Hs, let's say, which was the steady state level, and from there it will grow up to this, and then it will overflow. On the other hand, if I just go for this sort of input, t, if we reduce the input, okay, so this is Fi, and here this is minus a negative step if I give it, So this H prime like this and this. Okay. So this is 0, H prime here it will be 0, H prime is 0, and here H prime is equal to minus of Hs. So from here it will run dry after this some characteristic time, and which we can solve knowing the area and knowing the step height. Okay. So this there is a confusion maybe. So let's not use this capital A here. Let's use small a. So if it is small a step height, and this is Kp into small a into t, right? This step is small a into t, and from there we have got the implication that if I increase the inflow rate, the tank after some time will overflow, and if I reduce the step height or if I give a negative step, the tank will run dry after some time. So that is the implication and the physical analog of this type or the case 1 first order system. Next we will go for understanding the case 2 and its physical origin. So in case 2 first order system, we will have 2 constants because A naught is not equal to 0. So if I divide the equation entirely by A naught, I will get a constant associated with dy prime dt as A1 by A naught and another one which is B by A naught. So it is like A1 by A naught dy prime dt plus y prime equal to B by A naught f prime t. Right. So we call this constant as tau p, which is technically known as time constant. We will try to understand the physical interpretation later. So tau p is time constant, Kp is called the steady state gain, static gain, or gain of the system. Now we go for the Laplace transform. So here the initial condition at t equal to 0, obviously y prime 0 is 0. So tau p into s plus 1 whole bracket y prime is equal to Kp into f prime bar s. So the transfer function of this case 2 first order system, so this is case 2, A naught is not equal to 0. So Gs y prime s by f prime s becomes Kp divided by tau ps plus 1. So any process after Laplace transform of this equation, if it is 5 divided by 3s plus 2, so you can write that Kp is equal to 5 divided by 2 and tau p equal to 3 divided by 2. So for this again we are giving a step input. So let f prime bar s is equal to A by s, where A is the step height. So y prime bar s Kp divided by tau ps plus 1 into A by s. So it is Kp into A divided by tau p 1 by s minus s plus 1 by tau p. We are taking tau p common. So here it is 1. So you see what will happen now. that additionally we have a 1 by tau p here, so we have to multiply it by tau p, so this tau p and this tau p cancels out. So we have got this simplified Laplace domain output expression, and we have used this typical partial fraction such that we can easily convert it to this time domain response. So by inverse Laplace transform, y prime t kp into a 1 minus e to the power minus t by tau p. So this is a typical exponential growth we have here. So what was our input? It was a step function, and the output, see here, y prime infinity, what we get is kp into a, that is the final steady state or equilibrium value. So it will be like this. Okay. So it's y prime t, this is kp into a, and this is t equal to 0, this is axis t. So it's a exponential growth. Now from this response perspective, we have to understand the physical meaning of kp and tau p. So physical interpretation of gain. What's that? See, f prime infinity equal to a. Inputs infinite time after the value still remain a. F prime 0 is 0. So delta of f prime defined as f prime infinity minus f prime 0, the final difference is a. Whereas y prime infinity is a kp and y prime 0 is 0. So delta of y prime defined as y prime infinity minus y prime 0 is a kp. So essentially the ratio of the change of output to the change of input between two initial and the final states, right? So delta of y prime by delta of f prime, that is basically the change of input between initial and final states divided by change of output and change of input between the same initial and final states, that is gain. Okay. So this definition of gain is universal, that is valid for all systems. It's not only specific for first order systems. The same definition, that change of input between initial and final state and divided by the change of output between initial and final state divided by the change of input between the same initial and final state, that is gain, and this is true for all systems. Okay. Next we will go for understanding what is time constant. Now unlike gain, time constant is specific to first order process. We cannot have time constant of a second order or third order process, right? So, time constant is specific to the first order process, that we have to note and remember. It is very important understanding. So, here the physical interpretation of gain we have discussed. Next, it is time constant. What is that? Now, you see the time constant tau p. What was the equation? Y prime t a k p 1 minus e to the power minus t by tau p, and y infinity, that is the final value of y at final state, or y prime at final state. Alternatively, it also indicates the completion of the process, and that's equal to AKP, right? That means when the output's deviation y prime is reaching this value of AKP, we can state that the process is complete, okay? And that needs this infinite time theoretically. Now, y prime at tau p, which is AKP into 1 minus e to the power minus 1, and if you calculate this fraction or this expression, it will be 0.632 AKP. Now, AKP indicates, 1 AKP indicates the completion of the process, and 0.632 AKP indicates 63.2% completion of the process, right? So, this is indicative of 63.2% of the process is complete, right? So, we can define time constant as characteristic time at which 63.2% of the process is complete. Right. So, we can say that for any first order process, its time constant is that specific characteristic time at which 63.2% of the process is complete. So, there is an alternative definition as well of the time constant. So, let us also discuss about it. And it is based on the rate of the process. So, what is the rate expression here? Definitely the rate is dy prime dt. So, alternative definition of time constant. So, you see this y prime t a k p 1 minus e to the power t by tau p. So, dy prime dt is a k p minus 1 e to the power minus t by tau p into minus of 1 by tau p. So, finally, it becomes a k p by tau p into e to the power t by tau p. So, initial rate dy prime dt at t equal to 0 is a kp by tau p. So what it physically means, see. So this is a kp, this is y prime t, and this is the first order process, right. Now, if I think of initial rate, it is basically the slope of the tangent. Now, alternative to this actual process, we can think of a process like this. This is the process path. What is that? If the process, so this is the process, if the initial rate of change is preserved, right. This is not a first order process, but a hypothetical this analogous process where the rate of change remains constant, right. So it's retaining its initial rate and it's reaching the completion, because AKP attainment of y prime indicates the process completion. So this completion is being reached at t equal to tau p. Why? Because the slope is AKP by tau p. So we can propose an alternative definition for the first order process like that. If a first order system retains its initial rate of change, then it will attain its completion at t equal to tau p. Right. So this is an alternative definition, that if a process retains its initial rate of change, then it will reach its completion at t equal to tau p. So with that, that's the understanding of the dynamic response. Now we have to think about the physical origin of case 2 first order process, right. And elementally, what are the components upon adding which in series we get a first order process, that we have to understand physically, right. Searching the type from different domains, like from this hydraulic, from thermal, from mechanical, from electrical, etc. Everywhere we will show you that what type of systems actually exhibits first order behavior. Okay. So physical origin of first order processes. Number 1, hydraulic, or rather it's a storage tank fitted with a linear valve at its outflow or in its outflow line. So the example is something like this. Linear valve means F is equal to H divided by R, where H is the level in the tank and R is the hydraulic resistance, and this is Fi. Area of the tank is A. So A dH dt equal to Fi minus F. So A dH dt Fi minus H by R, or AR dH prime dt, directly we can write it in terms of deviation variable plus H prime is equal to R into Fi prime. So you can understand from the structure that this will exhibit a first order response, which tau p is equal to A into R and Kp is equal to R. Right. So if you change the flow rate Fi, and you can see that if you take the Laplace transform, H prime divided by Fi prime bar S is equal to R divided by AR S plus 1. Okay. So if you change this Fi by a positive step, so definitely we will have exponential growth of this level, and it will saturate to a value of this R multiplied by the step height. Like Fi, if you give a step height of small a, the final H prime will be R into small a. So that is the storage tank. Next example, mercury in glass thermometer. Right, it's a mercury in glass thermometer. So here we assume thermal resistance of mercury and thermal capacitance of glass are negligible. That is, thermal resistance of mercury, MCP mercury, thermal resistance of, sorry, this is the capacitance of mercury is much higher than MCP glass, and 1 by H mercury, there is a thermal resistance, is negligibly small compared to 1 by H glass. So if I have this thermometer, the temperature of mercury is T, outside temperature Ti. Temperature of the mercury is T and outside temperature is Ti. So, and additionally this is Hg, let us call it Ho, and see, if this is the, if I enlarge this is glass. So here we have Ho and here we have Hi. So Hi is equal to Hm and Ho equal to Hg, right. Or the overall resistance, here this is resistance of glass, right. So overall the heat transfer coefficient of the inner side, right, that's basically will be the overall heat transfer coefficient. Okay. So anyway, we simply consider this overall heat transfer coefficient is U. So we can write this if we consider as output and Hi if we consider as input, then mCp dt dt is equal to u into A into Ti minus T. Right. So basically, in deviation variable, the form remains intact. So we have dt prime dt as mCp divided by ua plus t prime is equal to Ti prime. So time constant is mCp divided by this ua and gain Kp is equal to 1. Right. So you can understand that if I consider the thermometer's mercury temperature as our output and the surrounding temperature as the input, we have the gain 1 system and mCp ua is the time constant. So it is pretty obvious that as time constant increases, with the increase of time constant, we have higher sluggishness of the process. Like example is, this is say the gain in both cases remains same and they are given with the same step change. So this is a process of time constant tau 1, this is another process of time constant tau 2, right. So tau 1 is much smaller than tau 2 because process 2 is a sluggish process where process 1 is a fast process. So you see that mCp increases or mass of the mercury increases or UA decreases. So time constant tau p increases. Right. So means if we increase the mass of the mercury, definitely it will take higher time of response to indicate the final temperature or to acquire the final temperature, right. So mercury in glass thermometer with negligible thermal capacitance of glass and negligible thermal capacitance of glass and negligible thermal resistance of mercury under this assumption behaves like a first order system. Okay. Next we introduce this system of RC circuit, where we have a resistance and a capacitor which is connected to a voltage source. Resistance is R, capacitor is C. Now applying this charge Q, accumulated charge, output, say this is ET, voltage is the input. So we have to do what? We have to apply KVL, Kirchhoff's voltage law. So we get R into I plus this Q by C is equal to E. Right. Now R is the rate of charge transfer. So R into dq dt into C plus Q is equal to E. So RC dq prime dt in deviation variable form, E prime is equal to Q prime is equal to E prime. So this is a first order process, tau p equal to RC, and this will be C here, and Kp is equal to C. Right. So that's the electrical example. And next, an example we introduce from another system which is called dashpot. So what is the dashpot? So the system is spring dashpot, spring and dashpot connected to a massless plate. Now what is a dashpot? Dashpot is a theoretical object quite similar to what we notice in door closures, right? So in door closure you see that when the displacement, like here we have a door and this is the door closure, let's say. So if I open the door at this point, it moves with higher velocity. As it comes closer to this position, steady state position, its velocity progressively decreases. So what is that? See, the dashpot system, basically we can understand that we have a cylinder. This is a theoretical system, hypothetical conceptual system. Actually the door closures are not like that, right, but pretty similar in structure. A cylinder is divided into two parts and there is a capillary here, its diameter is d and the diameter of this cylinder is capital D, and this space is filled with a viscous oil. Right? Now when we apply a force on this piston, dividing piston, which divides this to the entire cylinder into two compartments which are alternatively sidewise connected by a capillary, right, of diameter d, what will happen? The oil, as the piston, it can only move to right hand side if oil is moving with an equal amount of its volume displacement through this capillary. Correct? So let's calculate the velocity of oil through this capillary, how it is related to the force. So if the velocity is v, we know that here we can apply this Hagen-Poiseuille's equation stating that delta p is equal to 32 mu L v bar divided by d square. Right. So this is 32 mu L v bar by d square, Hagen-Poiseuille's equation. So this v bar is the velocity of oil through this capillary. Now what will be the velocity of oil in the main cylinder? We can apply the pipe continuity equation, that v bar into pi by 4 d square is equal to u into pi by 4 capital D square. Right. So v bar is equal to capital D divided by small d whole square into u. So let's replace it. So delta p is equal to 32 mu L by d square into capital D divided by small d whole square into u. Now what is capital this delta p? Because of this force, there is a difference of pressure on this side and this side. So force divided by cross sectional area we can write as Ft divided by pi by 4 d square is equal to 32 mu L divided by d square capital D by small d whole square into u. So you see that this 4 will be going to here, 4 and 32 giving 8 capital D square. This d is going cross multiplied here. So Ft becomes 8 pi mu L, where L is the length of the capillary, So capillary length is L. So 32 and cancelling out after that 8 pi mu L, and here d to the power 4 and here capital D. So capital D divided by small d whole to the power 4 whole bracket into U, right. So we call it Ft is equal to some mu star into U, and U is what? If I fix a coordinate, let us say y, right, where the position of the piston initially is y equal to 0. So you can write that mu star into dy dt. Ft is equal to mu star into dy dt, and mu star is this entire constant, right. It is pretty similar to this Newton's law of viscosity. However, there was a gradient in Newton's law, here it is time derivative. Now, if I think of a spring, this is spring and this is the dashpot. It is a typical schematic representation. Both are connected to a plate, right. The plate has got mass 0 and this is being pulled in the outer direction by a force Ft, and Ys is equal to 0, this is y. So you see, when Ys is equal to 0, a spring has got a spring constant Ks, the dashpot, this characteristic constant is mu star. So obviously we can write there will be a force balance, right. Or rather we can write that m into dy d square y dt square, it's equal to 0 because the plate has got no mass, this m is equal to 0, right. It is Ft minus Ks into y prime. Why y prime? Because y and y prime are same as Ys is equal to 0. The prime represents here the deviation variable. So y prime is basically yt minus ys, and this is equal to 0, right, minus mu star into dy prime dt. So what we get is something like Ft, and initially when there was no force, this Fs is equal to 0, so Ft and F prime are same. So this is mu star into dy prime dt plus Ks into y prime. So accordingly, we have this mu star by Ks into dy prime dt plus y prime is equal to 1 by Ks into F prime t. So this is also a first order process. Time constant is mu star by Ks, and gain Kp is equal to 1 by Ks. So in all these cases we have got a first order. Now let us actually go for element wise physical understanding of those systems. Element wise, if I go, just try to understand that initially we have started our discussion with a storage tank fitted with a linear valve, right, and the rate equation is simply matching with that of Ohm's law, like Ohm's law means potential difference divided by resistance is equal to the rate, and there in this tank the potential difference is H. Why? Because inside the tank the level was H, outside the level was 0. So the difference is H minus 0, that's equal to H, and the rate was F, which is H divided by R. So it's fine. Now the point is, this valve actually resists the flow. Okay. the valve actually resists the flow. So, first is storage tank. See, this was the system. Sorry. Now, we have to identify the tank storage device or storage element for liquid, right. So, it is basically a capacitor. Valve, a resistor element or resistance element to flow. So, it is a resistor, right, and the tank and the valve, they are connected in series. So, it is a capacitor plus a resistor in series. Now, let us think of the second, a thermometer. Mercury in glass, thermometer. What was that? We have this column, this bulb, here we have mercury and the mercury column, right. Now, glass is resistor to thermal energy flow, and mercury is the storage element for thermal energy. So, combine, because we have neglected the resistance of mercury and capacitance of glass. So, it becomes capacitor mercury plus a resistor glass in series, right. And what was the equation? The equation was mCp dt dt equal to u into a Ti minus T, right. So, if I think of a tank and an inflow tank, in this region, which has got a level Ti, right, area infinite, and it is connected to this tank through a resistor R, which has got a resistance of 1 divided by UA. This is T and area is MCP. See, the same structure is identically giving the mercury in glass system, because here we can write area A into dH dt is equal to, say, this is H, this is H0, this is R, and the area is A, okay, or small a, because A we have already used here. So, small a into dH dt is equal to this H0 minus H divided by R. So, what you will get? MCP dt dt is equal to Ti minus T0 divided by 1 by UA, the same equation as that of here. So, we can actually draw the analogy, right, and mercury in glass we can map in terms of storage tank, which is receiving its delivery from an infinite cross section storage tank. Why infinite cross section? Because surrounding is of infinite heat capacity and mass. If you abstract and give some heat to the surrounding, its temperature is evidently not going to change. So, that is why in tank analogy it must be considered as a tank with infinite area, cross sectional area. So, this is again a resistor and a capacitor system. Next example, the RC circuit. Obviously, the RC circuit, you can understand the R, here it is direct resistance and C capacitance, or R resistor rather, R resistor, C capacitor. There is nothing else to say. And finally, spring dash part, spring, mechanical energy capacitor, it stores the mechanical energy, and dash part is a resistor to the flow of mechanical energy. So, overall, from understanding all the different systems, what will be our conclusion? Case 2, first order system is actually consists of a resistor and a capacitor in series. Whereas, you see in the case 1 system, if we replace this, replace the valve by a pump, right, F is equal to F naught. So, it is a constant element and only we have a capacitor, nothing else. Alternatively, case 1 first order systems is a pure capacitor. Right. So, it is a pure capacitor and it actually has got no resistance element. Whereas, case 1 first order system, they are the combinations of resistance and capacitance in series. Now, in this first order system, we will discuss our final topic, that is first order system with variable time constant and gain. So, how come it becomes variable? We have to note and have to understand this. How come it becomes? It will become a first order system with this variable time constant. See, we have seen that we several times we have to apply the linearization, because most of the systems of real origin, they are nonlinear. So point of discussion is first order systems with variable time constant and gain. So let's directly go by an example. That is A dH dt is equal to Fi minus beta root h, non-linear valve. Right. So as the valve is non-linear, we have to linearize it. So A dH dt is Fi minus beta root hs minus beta by 2 root hs h minus hs. So steady state equation A dHs dt Fis minus beta root hs minus 0, because h is equal to hs. So if you subtract, we will get A dH prime dt is equal to Fi prime minus beta 2 root hs into h prime. So we have 2a under root of hs by beta into dh prime dt into dh prime dt, see, shift it to this and multiply, plus h prime is equal to 2 under root hs divided by beta into Fi prime. So by definition, tau p is equal to 2a under root of hs by beta and kp is equal to 2hs by beta. So what is important to note here, that hs depends on our specific situation, right? As we go on changing hs for different initial states, we will have different gain and time constant. So it's not only the system specific parameters, it's only specifically dependent on the process. So last example we see here, this is called a surge tank. So you see it is a tank. Sometimes you will see in process industry, particularly in gas line, that sometimes we have a tank. So that tank is not storage tank specifically, but surge tank. Surge tank actually it's helpful in damping down pulsations, right? Say in a gas line, specifically a steam line maybe. So there is a valve, a control valve, and suddenly by mistake you have closed or opened, or particularly you have closed the control valve because there is some safety issues in the downstream. So once you close that valve, there will be a back pressure being developed at this upstream of that pump, and which will propagate throughout the entire pipe network of that in the upstream section of that valve, right? And this is at every corner, every edge, and wherever we have any small devices, there will be vibrations, and that is called steam hammering. So in order to reduce this hammering or pressure pulsation, similar types of phenomena, we feed the surge tank in this process line. So let's have a surge tank where the pressure is P, volume is V, inlet valve is a linear valve Ri, upstream pressure is Pi, and we have RO, we have the pressure, downstream pressure is PO, and here it is QO, right. So if we consider incompressibility, so dm dt is equal to rho into dm dt rho into Qi minus Qo, and m, if you consider further the ideal gas, you see the ideal gas is m divided by capital M RT. So, P m by RT into V is equal to m, right. So, V is constant, so we can have mV by RT dP dt, the pressure dynamics in the surge tank we are trying to solve. So, this is equal to rho and Qi is the upstream potential difference, it is a linear valve potential difference, it is Pi minus P divided by Ri minus P minus Po divided by Ro, right. So, mV divided by RT dP dt plus, you see that what are the input? Pi is the input, Po is the input, right. P is the output of that system. So, we are not going for this which one is disturbance and which one is a manipulated variable. So, let's actually Po is the manipulated variable, Pi is definitely the disturbance. So, it is rho within bracket 1 by Ri plus 1 by Ro into P, and here rho by Ri into Pi plus rho by Ro into Po, right. So, you can have this divided. So, mV by RT rho 1 by Ri plus 1 by Ro dP dt plus P is equal to rho by Ri total divided by rho will cancel out. So, it is 1 by Ri 1 by Ri plus 1 by Ro into Pi plus this 1 by Ro 1 by Ri plus 1 by Ro into Po, right. So, this is a typical first order system with two input functions, right, and tau P is equal to mV divided by rho 1 by Ri plus 1 by Ro, Kp1 for the first input, it is equal to this 1 by Ri, or rather what we can write Ro divided by Ri plus Ro, and Kp2 it's Ri divided by Ro plus Ri. So, that is also the typical example of first order system with two input functions. So, if I think that that P naught is a constant parameter, so it can be dropped and it will be dropped in the deviation variable form of this equation, and finally we will get this term plus this term equal to this term. So, Po is being dropped because there is no variation. Definitely it is there, but if once we write the steady state equation, this is dPs dt which is 0 plus Ps, this Pis plus this into Po. So, if you subtract, this last term will cancel out and we will get the deviation variable form dP prime dt, here P prime and this constant into Pi prime, this term will be dropped. So, as a consequence we will have the typical first order system with one input and one output. So, that is all about the first order system. In the next session we are going to start and discuss about the second order and higher order systems. Thank you.